So for the remainder of this talk, I'm going to just give a live presentation in a Jupyter Notebook of setting up some different patches and taking you through the basics of using the Combinatorial Audio Workstation to make some cool sounds. And yeah, so I only found out a couple months ago that it's possible to do Rust in Jupyter Notebook. There's a library called EVXCR that makes it possible, which is pretty cool. It's a Rust REPL. And I was originally the video that I submitted for this is a live coding session where there's multiple different cells with sound in each of them changing over time. But I think for this talk, we're just going to keep things a bit simple and go through the basics. And by the end, we'll have something that sounds pretty cool. So this is just some boilerplate, which I've already run, that creates the output node and the shift button. Just so that we don't blow up the speakers. We're using my laptop speakers, so it doesn't really matter. And let's start with something simple. So the primitive type that all of the modules in the synthesizer implement is this SIG-P trait. It's just things that can be sampled. Modules are sampled not at the audio sample rate, but once per what I call a frame. You can change the length of a frame. It's usually maybe about 20, 30 times a second. And this sample method populates a buffer of the appropriate size given the frame rate and the sample rate. It's done that way so that we can take advantage of some architectural optimizations. So let's start with a simple hello world. Everyone's first synthesizer patch. We'll just play a sine wave at 200 hertz. It's already playing, but I've muted it. The 200 hertz sine wave. Let's turn the volume. It's already up pretty high. Oh, it's okay. Sine waves are high. We can change the waveform by changing this to a different value. It's a little bit cumbersome to change the number, so instead one tends to use a knob. And this is going to pop up a new window. Now, you'll notice that there's a lot of this build after everything. And this is because most of the modules in this library have optional parameters, same defaults that you can specify if necessary. And using a builder pattern in Rust makes it a lot more ergonomic. Only add the methods that only change the properties that you want to change and leave the other ones with their default values. So one example of that is the pulse width of the pulse wave form. So we change our waveform to a pulse. Now and so a knob is also a system that just always yields the position of the knob. And so this works because we can obviously put a fixed number in one machine. It's not going to be and the reason why we can exchange numbers and ones is, of course, because almost all of the arguments to parameters modules here's a more complex example. So here what we're doing is there's two oscillators. There's the pulse wave oscillator, the automated oscillator, using the sound. The second oscillator is modulating its pulse. And so this knob is controlled is modulated in my house. Not getting faster. Now we can do arithmetic on signals, and this will just do the corresponding operation on the pairs of values on either side of the arithmetic operator. And this makes it really easy to do stuff like make a mixer. So here we're just creating two oscillators, a saw wave and a pulse wave. I am using a shorthand here rather than using the oscillator function as a helper that just creates the wave of the given shape. So this is a pair of oscillators added together, roll over this, and then and has right, and the output is multiplied together scale. We'd be doing what's called FM. One way can act like aria, and the other way to modulate that. I mean, listen really into the sounds as well. Especially when the frequencies are very similar to that. So one particular beat pattern that's very common in is when you take a pair of saw waves very similar to these here, add them together. Every time I reevaluate a cell, it goes to a family of where interference sounded very different from a single wave on the phone. See how different it is. Let's play this one by kind of going down. It's an entirely new text. It's common that I've got to have a superstar of its which creates a set of waves at a configurable number. And performance reasons that some the see, it gets quieter because the number of waves interfering with each other destructively reduces the average wave. Again, it might have more possibilities. Okay. So the next concept to introduce is filters. We've already seen examples of signals that are modulated by other signals with output modulation changing. And to help make this kind of signal, I don't make it have a signal which is fully in the process, which then produces a new signal by modulating. Core has a method called filter, which you can use to chain together a sequence of transformations on the let's look at a simple example of that first. Bandpass filter. We're gonna make 100 hertz saw wave, and then pass measure. Filter has to note as a little harmonic format down by outside of its if you think of the FFT would look like you're kind of standing down with and then moving outside as not all the way down. All you hear are bass harmonics, or the bass frequencies from the waveform. Instead of that, move to the higher, change the filter to be very narrow. It's a shame. Oh, I guess we can turn the volume up. So when you make it really narrow, you can isolate individual harmonics, and so you can see the different harmonics of the saw wave one at a time. It really helps you understand more about bias the wave sampling it does, and you look at the frequency, you look at the formula for how to draw a saw wave, and you see that it's made up of different integer harmonics. And now you can listen to them one at a time. Let's look at another example. This time we're going to use a low-pass filter. They're very similar to the bandpass, except now it only removes the high frequency. The reason I introduced that pin is because it's a second knob controlling the resonance, which you imagine a filter removing everything above its frequency. It can also add a little boost to the frequency around that quite common in the pass filters used. I also don't know if this is an implementation artifact or sound aesthetic. See more of that in a second. The final one is a little more complex. So we're going to take the previous example with our oscillator going into a low-pass filter, except instead of the saw wave, we're going to use a saw wave. And then this final filter I'm adding is a compressor. The behavior of a compressor is to clamp all of the very common in synthesizers to automate things kind of signal which reacts to a button press and sends a pulse of a certain shape as though a knob was being turned by that. So I'll run this example and then explain what's going on. Okay, so this time we have a button. When I press the button, I'll turn the volume up a little bit. So this envelope has two properties called attack and release. The attack controls how long it takes for the signal to ramp up to its maximum value, and the release controls how long it takes for the signal to ramp back down to 0 when the button is released. So if I turn the attack up, and I turn the release down, and then I press this button, and then when I release it, it cuts out immediately. All right, if I was to return the attack down and the release up, we see the opposite. And so you can use these settings and others to change the way that a note comes on or off when a key is pressed on a keyboard or a sequencer chooses the next note. So rather than pressing a button manually, as we just established, we like to automate things. So here we're going to automate button presses with a clock. So 8 times a second, this clock will send a pulse to an envelope, which will modulate a supersaw wave. And we'll get some knobs that we can use to control the properties. But the windows take a little while to start sending signals back to the synthesizer. Still uses meaning internally, by the way. Every window is a different process. By sending meaning commands, it seemed like the most cross-platform way to do. is that you'll notice there's no attack anymore, just release, and that's because the button press is being automated with the plot, which is just sending a pulse, which means that the attack would have to be 0, or we wouldn't hear it. We wouldn't be able to ramp up control the release. Release down the length of the notes. For constant washy sound. All of our sounds from scratch every time. There's a couple of handy built-in patches that to every for things that are a bit more complicated than melodic stuff like we've seen so far. So drums, rather than using pre-recorded drums as an option of synthesized drums, really just has 3 right now: kick drum, snare drum, and a hi-hat. I'm just looking at those first 2. So is it very quiet? Turn that off. We have snare. They're also quite parameterized. I don't know how. Is Jupyter going to let me autocomplete? Okay, I don't remember the names of the parameters, but there's lots of settings you can change about the way these sound if you want to tune them for a specific application. And of course, we don't like pressing buttons, so it's very easy to automate these. This button is obviously just a signal that produces a Boolean, much like our clock from before, so we can do the same thing as earlier. So now, this is just setting a, so this is using the concept of a clock divider. Is that okay, cool. So skip on to the sequencing. So to play actual songs, could play them manually, but instead let's program in a sequence of notes and then send those set those to be the frequencies of the oscillator. So I've pre-programmed a riff that I kind of like. So just using the triangle wave, a simple ADSR. Exciting. It's showing how we notes, and then we can turn those notes. And then if you take everything we've seen so far, I think that's all we have time for. So just put there's a bunch. Obviously, we're only scratching the surface. We can do with cool. But yeah. Thanks everyone.
I'll wait for our last answer. How is that one question? More on the machine.
Yes.
Would you briefly compare with Super Collider and tell us maybe, I saw that you were referring to FRP and how FRP differs from the graph version of Super Collider.
I've honestly never used Super Collider, necessarily.
Yes. But yeah, can you tell us about how FRP can be applied for that?
Sorry. Yeah, totally. What's the
I know what's going on. Wait a moment.